Hi, I'm Emerson. I'm in the thermodynamics class. Today I'm going to try to reproduce one of the experiments that was shared on CCLE. So we have an aluminum can here, which is warming up as I speak, and we have a bowl of room temperature water here. So the goal is to sort of demonstrate that as I put the can in, as it's been extremely heated, I think the first run that I did, it got to about 500 degrees Fahrenheit. So we're going to, once it reaches about that and gets pretty much red hot, we're going to put it into the water, but we're going to put the opening side, the drinking side, down so that it encloses our control volume and so that there's no escape of gases. And the water being much, much colder than the can at the time, and the air inside the can, we expect some conduction, and so those gases will reach thermal equilibrium with the surroundings so rapidly that it'll cause a contraction of those gases, and we hope to see that the can is actually crushed because of the decrease in pressure inside. So we'll see that the work done by the surroundings on the can is related to the fact that there's atmospheric pressure, and due to the really quick cooling of the hot air inside the can will cause a decrease in pressure, and that gas will try to reduce in volume, and it'll bring the exterior walls of the can with it. So while that's getting warm, I'll talk about, I first found the volume of the can. I didn't read what was on the side because they don't always fill it to the top. That's how they get you. So I filled it up to the brim, and then using a scale, I measured the weight before and after I filled it to find the difference, to see how much water I added in weight, and then using a density chart I found online, the density of water at about 85 degrees, which is what it is today at my house, and about 1 atmosphere of pressure. I found that value and then used the density equation for mass over volume to find the volume to be about 372 cubic centimeters, which is actually 20 more cubic centimeters than what it says on the can. So it was a good thing I did that, and I'm hoping to find the volume after contraction by refilling it with water, redoing the same process I just described to find how much weight or how much volume is still available inside the can. So that should be the same volume that after the thermal contraction occurred, or after the work crushed the can, the work of the surroundings. We will see that the difference between the first volume and the second volume should be about the work done on the system by the surroundings, and we can calculate that later, and we can determine the change in internal energy of the air inside, and so on and so on. So we can be very quantitative in this demonstration. So the can is